Okay, welcome back everybody to the Symmetry seminar. This week it's a pleasure to have Andrea Ferrari, who will tell us about non-invertible symmetries and higher representation theory. And please do ask questions, because in this case I'm not allowed to. So, Andrea, take it away.
Yes, so thank you very much for inviting me to speak here. It's really a wonderful series of seminars. So today I'm going to talk about connections between non-invertible symmetries and higher representation theory. This is based on joint work with some people in the Durham group, namely Matthew, Thomas Barsh, and Jamie Pearson, who are two great PhD students. So as an introduction and motivation, there has recently been a lot of excitement around non-invertible symmetries. They are ubiquitous in QFTs. We see them show up everywhere. There are generalizations of the Cramer's Wagner effect in higher dimensions. There are some non-invertible symmetries that arise from discrete gauge theories, even pure gauge theories. And we are starting to see many physical important applications of these non-invertible symmetries. For example, Hardy formulas for counting states in the DCFTs have been proposed that use and exploit non-invertible symmetries, or even pion decay has gained some insights based on non-invertible symmetry consideration. Now, in general, in a d-dimensional theory, we expect topological defects to form a d-1 fusion category. So in general, this is what we would expect our non-invertible symmetries to be generated by. But these categories may be quite intricate, and this can make it very difficult to unleash their full power. So one of the motivations for this talk is to answer the question, can one systematically construct theories in some ways whose non-invertible symmetries and the respective d-1 fusion categories are completely under control? Now we know that when we have, that we can produce non-invertible symmetries, especially what are now known as non-intrinsically non-invertible symmetries, by means of some gauging procedure. And there are a variety of things that we could do to produce them, and they have appeared in a series of fantastic papers. For example, we could gauge a discrete symmetry with some Toft anomaly, or we could gauge a non-normal finite subgroup of some global symmetry, or we could gauge a higher form symmetry along some higher codimensions of manifold, which is connected to the notion of condensation defects. Or we could, for example, gauge some symmetry along with some lower dimensional TQFT supported on some submanifold. Now, there are some very special cases or a subset of these where we actually know what the category we end up with is. And this is work that goes back on 2D QFTs that goes back quite a long time. And for example, if you gauge a finite group G in 2 dimension, you expect the resulting theory to have Wilson lines that fuse according to the representation theory of G. And if G is non-abelian, we may obtain non-invertible symmetry with symmetry category rep G. So what I'm going to propose today is that we can embed all these gauging approaches to non-invertible symmetries in a general framework where we take a d-dimensional theory with a finite d-1 group symmetry G, perhaps with some anomalous, non-anomalous to group S. We gauge S, and we get a d-1 symmetry category related to the higher representation theory of S. And in particular, I will focus in this talk on a special case of this phenomenon. So I will work in 3 dimensions, take a finite anomaly free to group G and gauge the whole group. And what I'd like to show is that gauging a two group in B3 leads to a two symmetry fusion category, symmetry fusion category that is the symmetry category 2 rep G. And moreover, I want to show that this applies to a large class of gauge theories. So this is then my overview. I will start with a lightning and necessarily very schematic review of what a two representation is. Then I will move on and explain to you how do we gauge finite groups and how do we get a symmetry category that is related to the representation theory or the two representation of this group in 2 dimensions. And then I will move on to gauging finite two groups, explain some gauge theory applications, and then make some remarks in conclusion and explain a little bit our outlook on this topic. So let me start by giving a linear review of two representations. So the idea is that we can view representations of a group as functors. What does it mean? We can view a group as a one category with one simple object, and a collection of morphisms, all of which are invertible. And these are the elements of our group. And the representation in particular is a functor that takes our object that goes in the category of vector spaces. So in particular takes our single object to a vector space, takes the elements of our group to some endomorphisms on this vector space, and where the intertwiners are given by natural transformation. So this is one perspective, that one categorical perspective that one can take on groups. So today we will work with two representations, which are a generalization of this notion. Namely, we will view, or we can view a two category, so a two group as a two category who's with one morphism and morphisms between morphisms, two morphisms, all of which are invertible. And then we can consider some functor with some adjectives that I'm not gonna explain in details, that takes us to a category of two vector spaces that represents this two group. So in order to make a connection to what is perhaps more known to physicists, so here we can take this two category and reconstruct from it a two group as we perhaps know it in terms of a zero form part and a one form part. And how we do that is via the notion of cross modules. Namely, we can extract from this two category one group that is the group of one morphisms, which we put here, and another group from the group of two morphisms that we can put here. And this can fit into a cross module where H again is what is known in physics as a zero form part and A is the one form part. And from these two groups, seen as a two category, we can reconstruct an action of H on A and a Postnikov class that basically classifies these two groups and cross modules. And so a representation theory, a representation of this two group will be a representation on a category of two vector spaces. Now there are various incarnations of two vector spaces, and for us, I will mainly take a representation of a version of these two vector spaces that appear, for example, in these papers here by Zorman, Kapranov-Wodowski. And two vector spaces can be thought of natural numbers, n, with one morphism n times m matrices with vector space entries. We can compose these morphisms by replacing the sum and product with direct sum and tensor product within vector spaces. And two morphisms will be collections of linear maps between those vector spaces. So in some sense, we are categorifying the notion of a vector space by, instead of thinking of collection of numbers with sum and product, collections of vector spaces with direct sums and tensor product. And this will be the framework in which we will build our two representations of our group. But before moving that far, let's start simply by looking at finite gauge groups and what their symmetry categories are, and then gauging this finite group. Unless are there any questions so far?
Sorry, what is the advantage of describing vector spaces of two categories instead of a normal one category of vector spaces?
So we are looking at a categorification of the notion of vector spaces. There are two vector spaces, and the data they are classified by is what I've given here. The intuition behind it is that you kind of lift up your notion of vector space where you have numbers that you can add and multiply in the ground field with vector spaces that you can tensor together and take direct sums thereof. So it's a categorification of the notion of vector space.
But also vector is a categorization.
Yeah.
So I'm asking why 2vec is like better than vec.
It's a two category.
Yeah, I see. Okay, maybe I will understand the goal.
Yeah, let's go on. So consider a theory T with a finite group symmetry G. So we can label the simple objects. So the simple objects are basically surface operators that are labeled by elements of G. And in particular, the fusion structure, so remember we are in 2 dimensions, will be the, in 3 dimensions, will be the, will follow the group law of the group essentially. So a general object will simply be a G-graded set where we have a collection of objects graded by the elements of G. And then we can take direct sums of these objects. It is basically the joint unions of these sets. We take the collections together and we build larger collections. We can take their tensor product that corresponds to the Cartesian product of these sets, where we have to pay attention to our grading. And so the one morphisms between these objects basically form the category of vector space on a given object, and the way in which these one morphisms of lines fuse follows the tensor product rule with some compatibility condition. And again, the one morphisms between these objects will be two matrices whose components are vector spaces, this time graded by elements of G, and the two morphisms would be collections of homogeneous linear maps between two matrices. And this is what people call the category 2vec G, the category of two G-graded vector space. Now we want to take this setup and actually gauge G. So how can we do that? One way to do that is to insert an algebra object. It is basically the direct sum of a collection of elements in G. And then consider networks of defects labeled networks of this algebra object that when expanded, they will be basically be equivalent to summing over background flat connections for the group we are gauging. And so if we want to talk about topological surfaces in the theory we have gauged, then we can talk about topological surfaces in the theory where we have not gauged, together with instructions about how this algebra object ends on the surfaces we had before. So in particular, if we decompose our algebra object into components, we can see how some components of our algebra objects, that here I'm labeling by H, end on configurations of surfaces that were topological in T. For example, here H will induce a one morphism between surface graded by HG and the surface graded by G. And similarly here, we will have one of these morphisms relating these two surfaces. Now, as I said, we need to look at collections or configurations of these networks of algebra objects that are compatible with the fact that we need to be able to move them around. And these compatibility conditions are best expressed in terms of a particular one morphism that I will call rho of G. This basically comes from putting together these two configurations here, with the result that we have a component of the algebra object piercing through a surface that was topological in T, which in case is the surface S. And this rho G will be the one morphism that we get in between here. And the study of the compatibility conditions leads to a particular classification of these topological surfaces. In particular, the objects that we end up classifying will be surfaces S, which will be indexed by natural numbers, and collections of n times n two matrices rho G, which are in the homomorphism between S and S, as I depicted here. And this data here will be supplemented by some two isomorphisms that tell us what's the relation between trivial line on S and the morphism induced by the identity element in A, and some other two isomorphisms that govern the composition in G.
I have a question.
Yes.
Andrea. So
Yes.
for the gauging of finite groups, so for the G, is it the group in the closed model or the physical zero form symmetry?
Sorry, I couldn't hear very well. Can you repeat?
Yes. So the group G, is it in the closed model, in the definition of closed model?
Now here it's just a simple a genuine group, finite group G. We are just looking at genuine finite group G.
So the physical zero form symmetry G.
Yeah, that's right.
But if you have a non-trivial two group symmetry, non-trivial polynomial class,
we are not talking about two groups here. It's just a simple group.
Okay.
There is no one form part. Yes.
I see, just a zero form.
Yes, that's right. Yes. And so if we look at all the conditions, this is precisely an object in the category 2 rep G. Remember that I told you before that we had basically objects labeled by natural numbers with n times n two matrices acting on them. And so this is precisely the notion of a two representation of the genuine group without any one form part G. So more conveniently, we can recast the data that we have in the following way. We have a G set S, where the action comes from this rho G, and a class in the second cohomology group of G valued in U1 listed by the G action S. And we can ask ourselves the important question, what is this more physically? Now, if the set S has cardinality 1, then C just determines an SPT phase on the surface. So we know very well physically what this is. If instead the cardinality of S is greater than 1, then our claim is that this represents condensation defects. To understand this claim, we can consider what the simple objects are. So since we have a G set, we can decompose this G set into orbits, and accordingly, we can decompose this class here into orbit pieces, so to speak. So here O is a G orbit, and we have a class in this group cohomology determined by the orbit. All we are doing is taking this G set S and decomposing it into orbits. And then by an orbit stabilizer correspondence, or also what is also known as a Shapiro's isomorphism, we can label G orbits by stabilizer subgroups of G. And correspondingly, we can take this class in H2 of G valued into 1O and convert it into a class in H2 of this subgroup valued in U1. So if we want to classify the simple objects in this category 2 rep G that we've got, we see that in general, we have objects where the bulk gauge symmetry is broken to a subgroup on the surface by partial Dirichlet boundary condition. And on top of this, we are stacking some SPT phase that is determined by this class here. That this, at least in some special cases, is a condensation defect follows from some recent papers of these people here. But we can gain some further insights into their condensation nature if we look at fusion of lines and simple surfaces. And I will explain this fact in a second. What I'd like to tell you about this category rep G, though, is that we can control it very well, which was one of the initial motivation that we had. In particular, we can start with the fusion that we had in the in 2-vec G, which was the symmetry category for the TODP, follow through what happens when we perform all these operations. And we can see that the fusion between simple objects basically become a higher generalization of what in representation theory are known as Mackey formulas for inductor and restrictor. I'm not going to go into too much technical details, but the important takeaway message here is that if we have two simple objects, we have a very concrete way in which we can describe their fusion, and the decomposition is labeled by this double cosets, and which tells us basically how to merge these objects together. Furthermore, the one morphisms between the simple objects have a very intuitive physical representation. For example, if we start and simply look at the homomorphism between the identity surface and one of these simple surfaces, where we broke the gauge symmetry to H, and we stuck an SPT phase on top, these will be lines that are somehow anomalous. We could call them anomalous Wilson lines that transform in some projective representations of A. And in particular, they live at the end of this surface whose SPT phase kind of reabsorbs the anomaly. And as I anticipated, the fusion between lines on the surface also illuminates this phenomenon of condensation. So in particular, we can consider this simple object, HC, take one of our topological Wilson lines, bring it to the defect. And what happens is that we will get the representation restricted to, so the line corresponding to the representation restricted to A. So if you gauge, if we break the whole gauge symmetry here, basically the line kind of becomes some copies of the identity line, disappears or evaporates, we could say. This is precisely what happens in condensation. So let me discuss very briefly a very simple example. So we take the gauge group G, which is Z2. It has two elements, one at X. And the simple two representations are basically determined by choices of subgroup, because in this case, the H2 class vanishes. And the subgroups are Z2 and 1. So you know, remember, these are the stabilizer subgroups. Here, basically, you have the full gauge symmetry preserved. And so this one here will be the trivial identity surface. Whereas 2 will be a condensation defect, because it will have so the group H will be basically a trivial group. We have a two-dimensional orbit. And using our techniques, we can compute this fusion very well. So 1 fuses with 2 fuses with 2 to give 2 times 2. And based on what I said, 2 is our condensation defect. And we can also compute the one morphisms, and we get back this very well-known picture where we have the identity surface here, the condensation defect here. We have our Wilson lines, which act as endomorphisms of the trivial defects. All the Wilson lines on the condensation defect can evaporate, leaving back Z2. And then we have some morphisms between these two objects. And this is basically all I wanted to say concerning the finite group G. And so, summarizing, we started with a theory with a symmetry G, studied its symmetry category, gauged it by means of inserting this algebra object, and we landed on the category of two representations of G. Are there any questions so far?
Could you repeat why do you think you get to rep G? I missed the argument. Like you think you get to rep G after gauging G. Right.
So basically, when we implement the gauging procedure with this algebra object, inserting this algebra object, and we look at all the compatibility conditions for this object here, and then we end up with a classification of the remaining data, and we look very concretely that this is actually 2rep G, what is known as 2rep G.
And what is your definition of 2rep G?
Yeah, so it's a representation of 2rep G in this category of two vector spaces, technical definitions that you define into this category. But the objects have been, for example, classified in these two papers. So our starting point was the classification of the objects in there, and we actually checked very concretely that we would get the same thing.
Hi, sorry, can I ask a similar question?
Yes.
So you describe algebra objects internal to the monoidal bicategory 2-vex G, right? So this is,
yeah,
you say algebra object, so this is like a pseudo algebra object internal to 2-vex G. Could I say that?
Yeah, I think that's right.
And then, so what I would expect is that I'm just trying to get my dimensions right. So if I take, for instance, vex G, right? So I take the ordinary G-graded vector spaces, then I can take the category of separable algebras and kind of intertwiners of these, and this would be equivalent to 2-rep G. Have you seen that? So this is like Etinghoff, this Etinghoff representation theory. So if I have the fusion category, then the bicategory of kind of algebras, bimodules, and bimodule homomorphisms would be the same as the kind of representation theory of this. Maybe I'm going off on a tangent.
Yeah,
maybe it's interesting. Yeah, maybe we can discuss at the end.
Yeah,
it's
I think it's something to be discussed at the end.
Yes. Yeah. Perfect.
Yeah.
But maybe, I mean, just I guess the philosophy is, as you say, Andrea, is like it's just you start with some theory with a G symmetry, and then you ask what are the topological defects after gauging, and well, they're the topological defects before gauging, together with instructions about how all these networks end on them, and then you just go ahead and compute that thing, and you can match it with.
Yeah.
So you're saying you actually explicitly want to do the true, like the bimodule calculation.
Yeah, I mean that's
Yeah.
essentially
Okay,
what
I see.
symmetry would
Okay.
do.
Okay,
Yeah.
cool.
Yeah. I mean, it's exactly. So now let's go on and talk about gauging finite two groups. So we can play a similar game now, starting with a theory T with a two group G. Now we have both the zero form part and the one form part. We have a Poznikov class and a homomorphism action that tells us how H acts on A1. And we again very concretely insert take the topological defect we started with, perform this gauging procedure, and we look at what kind of objects we are classifying in the end that will remain topological. So the game is very similar to before, and so very quickly we still have a set, which is an H set now, where H is the one form symmetry. We have some co-cycle valued here, and the one form part will instruct us to consider some co-characters with A that will set with some compatibility condition. So, for example, this C here is not closed anymore, and but the failure of it to be closed will be determined by the Poznikov class. Moreover, the H action, we have kind of two H actions of actions of H and A, or sorry, on the sum of on the collection of characters. One comes from the property of this being a G set, and one comes from the homomorphs in the row, and we want them to be compatible. Again, we can open our papers on two representations and actually check that this data here is the data for a two representation of G. And sorry, I think I said co-cycle, that's actually a co-chain. And okay, and so the result is that we get this two representation of G. The easiest case to describe, and this is the case I'm gonna focus on, is when G is a split two group. That is, theta is 0, and we have a homomorphic row of H that acts on A1. In this case, we can gauge in steps. So we can start from our group G and gauge the one form part. When we gauge the one form part, we will get back a group G hat, which is a genuine group. There is no one form part anymore. And we know what the symmetry category of this group here is 2 vector G hat. So we can take this as a starting point, gauge back to get G, and then maybe gauge H. And we know that by doing that, we are bound to, or this is what we want to check, that we're gonna get to rep G hat. And similarly, from here we gauge H, it's like gauging our group G and get the symmetry category to rep G. Now, the symmetry category T is essentially a higher analog of a semi-direct product. So remember, the symmetry category T is the symmetry category of that we have when you have this symmetry group G A1 cross H. So essentially, a higher analog semi-direct product between rep A hat and vector H. And basically, so we have things that like the representations of A, but they are graded by H. I'm not gonna talk very much about this case T. What's more interesting is what are the simple objects in E mod G, which is the theory that we get when we gauge the whole group here. And the symmetry objects in E mod G will be labeled by an H orbit O, or equivalently a stabilizer group in H. A class in H2 of K valued in 1, and a K invariant character. And so we can make some remarks concerning this piece of data. So the fusion, one morphisms, and composition of one morphisms are computed as essentially as for a ordinary group, in the sense that by following it through all the manipulations, we get two formulas that very closely resemble induction restriction formula for groups and the representations thereof. Another point that arises from this analysis is that one morphisms can only exist between simple objects. You can only if the respective characters chi live in the same H orbit. And the condensation is determined by whether something is a condensation or not, depends this time on the multiplicity of the orbits. So this is all a little bit too abstract, so let us look perhaps at an example. So we take the group G, group G, which has a 0 form part Z2, a 1 form part Z2 cross Z2, and the homomorphism rho, where the group X, the element X in Z2 basically exchanges the two copies of Z2. Now the characters for Z2 times Z2 are basically the elements in the Pendragon dual, which is isomorphic to the group itself. And we will denote them by 1, X1, chi1, chi2, and chi1, chi2. And we label each simple object by pairs of orbits in Z2 and chi. So we can list all the simple objects that we have. So we have things where we have the trivial orbit in Z2 and things where we have the orbit Z2. And moreover, we remember that we are, in addition, looking at characters for the one form part, which is on top, and doing this classification exercise, we get a collection of simple objects. And we see that we have a trivial 2 representation, a one-dimensional 2 representation with some character on top, 2-dimensional 2 representation with other characters, and then some condensation defects, and these are which are determined by the full orbit and the full orbit O and a collection of characters. Particularly here with the character chi appears twice, and so it has a multiplicity 2, so it's a condensation defect, and same happens for X1. So if we compute the fusion, we get a very nice structure. We see that the only invertible simple objects are 1 and B. You can see them here. And the important takeaway point perhaps here is that when we compute in this framework the fusion between D and D, we get back the condensation defect tensor with some of the other objects. And this is all implemented at the level of simple objects. In contrast to some earlier statements in the literature where this condensation defect here has to be kind of inserted a posteriori. And remember in our criteria about the existence of one morphism, this is the point that I wrote here. morphisms can exist between simple objects if and only if the respective characters lie in the same H orbit in A. We can see that basically morphisms can only exist between X and 1, the same characters here, and V and X prime. Sorry, V and X prime. And working them out in details, we get this representation here for the symmetry category. Again, on the trivial surface, we have the full rep Z2 surviving, whereas on the condensation defects, some of the Wilson line condense, and we get back Z2, and the same holds here.
Can I ask a question?
Yes.
What is the difference between rep Z2 and rec Z2 in this diagram?
Yeah, right. So rep is the category of representations of Z2, and rec Z2.
Yeah.
Yeah.
But how do you know which one was which? Like.
Right. So here we have, on this defect, we have the full Z2 gauge symmetry surviving. And so we had rep Z2, which are the Wilson lines for this gauge symmetry. Whereas here, the gauge symmetry is completely broken. And so the Wilson lines just become generators for a global symmetry, Z2.
But when it's not, you didn't use this physics argument to derive this picture, right? Like,
no,
I thought like at this stage, all you know is the composition of the morphism is like some Z2 thing. And how do you know the difference between those two?
Right. So so the mathematics computations, again, I haven't entered in the details here, but the fact is that this category of two representations of G is well known, and we can compute the morphism with simple objects very nicely. So in particular, we can start from, so we can compute the fusion between them. And if we can compute the fusion, then we can kind of take the opposite of one of the objects and can compute morphism between them. All I want to say is that there are very concrete mathematical manipulations that will tell you that this is actually what C2.
I mean, yes, the categories are the same, of course, but I think we just, from a physics point of view, we write rep of Z2 when they're Wilson lines, and there's an unbroken gauge symmetry on the defect, and we write vect of Z2 when the symmetry is broken on the defect, and they're just generating a global symmetry on it.
Yeah, that's right.
But it's a physical statement. Yeah.
I mean,
that's fair.
Yeah, there are. Yeah, you can. Yes.
Can
so
I ask another quick question?
Yeah.
Just trying to understand your setup in terms of anomalies. So if I start with a two group acting on your 3D theory, and I just look at the zero form part, and I try to make that a genuine action, then I'll probably come across an anomaly of these surfaces meeting, which will give me the obstruction, which is a 3 form. So this is sort of like a toothed kind of anomaly for that 0 form, which gives me a 3 co-cycle. And if you restrict it to H, then that 3 co-cycle gets trivialized by this class C. Is this how I should see what you're doing?
So I think so. I mean,
so your Postnikov class theta, which gives you the connection between the 0 and the 1 form,
yeah,
is so D of C is that theta. Is that correct?
Yeah, that's right. Yes.
Okay. Okay.
Yeah. I think that's perfectly correct. Yeah. As I said here, this cochain that's not closed anymore, but that's a modification there.
Okay. So this theta is sort of an anomaly to
yeah, I mean, you can view it this
the
way.
0 form symmetry.
Yeah, from a more categorical point of view, it's like, yeah, an associator for this.
Exactly. Yeah.
Yeah.
Yeah,
Thank
but I think we don't usually talk about the Postnikov class as an 't' anomaly, though.
But it is precisely that way of getting it, right? I mean, you will look at surfaces coming together.
Yeah, yeah,
That's true.
yeah,
It has something to do with associativity for the surfaces.
yeah. I mean, yeah, I think it's what happens is that your associativity for the surfaces holds up to something that is dictated by the Bosnikov class, and I fully agree with that. Yeah.
Yeah, that's very helpful. Thank you.
I think there's another question there. Ken?
Yeah, sure.
Yeah. Can I ask a question?
Yes.
If I understand correctly, at the level of mathematical definition, the one-form symmetry A1 can be non-invertible, right?
Sorry, can you say it again?
At the mathematical definition level, the one-form
Yes.
symmetry A1 can be non-invertible, right?
Yeah, I'm taking it to be invertible, to be honest.
Yeah, physically we expect it is invertible,
Yeah.
Abelian, but it
Yeah.
can be non-Abelian, right? Or maybe I said something wrong.
I mean, I would have thought it's always invertible, but I'm always taking it to be invertible. I don't know whether there are some.
I may have said something wrong. So the question I wanted to ask is, the mathematical level of the definitions, this one-form symmetry A1 can be non-abelian, right?
Non-abelian.
Yeah. Maybe I
Okay,
said something.
I mean, two different things.
And my question is, do you have some example?
No, I've only looked at examples where the symmetry is abelian.
Okay, thank you.
Yeah, I think we have another question.
Another question from Nick. Yep, go ahead.
And yeah, can you go back to like the diagram where you gauge like I think the automorphism and what was it again? Like the edge and the other one. Yes, this one. So, what actually can you maybe explain more a bit about what this is doing here? So like you have a one form symmetry, which is A, and then the automorphism edge.
Yeah.
Or what? And then you gauge you. Okay, so you basically you're saying that if you can gauge H and A independently.
Yeah.
That obvious that you can always do this, or is this
for this split non-anomalous split to groups? Yes.
Okay, and I remember maybe I misunderstood, but I thought Matthew told me like many months ago that you can get non-invertible symmetry from gauging some two group. But is it somewhere in this diagram?
These are two group in the sense that A checks on A.
Sorry, maybe let me phrase again. Do you get non-invertible symmetry from this diagram, or not, or should I not looking for it?
Well, yeah, there can be in the 2-rep G hat or 2-rep G, and I've just given you an example where this happens. Look at this example here.
I see. So
here the only invertible objects are.
So the condensation defect is
that's right.
not from there.
Yeah.
And this is coming from. Does this come already from gauging the automorphism, or do you gauge the whole thing?
No, you have to get the whole thing.
I see. Okay, thanks.
Right. So some gauge theory applications. We start from so we take a simple Lie algebra G and we look at the associated compact simply connected Lie group G. The automorphism to group is we have an automorphism to group of this group that's given by the center. It's like the one form part, and the outer automorphism of G, which is the zero form part. So G is the outer automorphism, set G is the center. And the pure G gauge theory, gauge theory has symmetries, zero form charge conjugation symmetry out G, and the one form symmetry set G generated by topological group of Witten defects. And we can gauge, again, as I explained earlier, these two grouping steps. One form electric symmetry is then traded for or with a magnetic zero form symmetry. So we can draw a diagram like this that basically is a gauge theory incarnation of the diagram that Nick and I have just discussed, where we start with this theory T with center symmetry Z and some outers G. So the outer for G. We can gauge the center and gain a magnetic one-form symmetry, or we can gauge the outer and go down here. In particular, the symmetry categories that we get are the two representations of Z, G, and South G down here, and two rep of this combination in this corner here. So as an example, we can take spin 4n. This was is an example that was considered in paper by these people here. And the resulting diagram will be a network of two gauge theories with different gauge groups whose symmetry categories we can control very well based on our consideration. In particular, the symmetry category for PO4N, pure PO4N, will be this the category of two representations of this group here, which is the one that we just discussed. And this brings me to my conclusions and outlook. So what we are aiming towards more generally is that if you have a theory T in the dimensions with some finite T-1 group and some anomaly, this theory will have some symmetry category that will depend on this anomaly. And what we can do is gauge some anomaly-free D subgroup H of G, and the resulting category will be some category that depends on this data, where we have inserted this site that tells us that our anomaly restricted to the anomaly-free H group G will be trivial in form. And we have several expected equivalencies between these categories. We can take D-1 vects. Sorry, we can gauge nothing and can vect, or we can gauge everything and get D-1 rep. And there will be many steps in between with various combinations. And this will have to interplay with with all these gauging procedures that I listed at the beginning, and provide a systematic framework in which to understand them. So to conclude, a few minutes early, but the higher representation theory provides an efficient framework to investigate these non-intrinsically non-invertible symmetries. So this is just the beginning. The mathematics is being developed in parallel. For example, if you start browsing the literature about three representations, things become much more sparse somehow, at least the very concrete ones. And these kind of perspectives will also probably be helpful when thinking about the consequences of non-invertible symmetries, including action and non-topological defects. So we have some work in progress on all of these topics, and so stay tuned more anon. And I put here my talk. Thank you very much for having listened to it.
Okay, thanks. Let's thank Andrea. All right, questions?
Hi, Andrea. Thanks for the nice talk. So I just want to ask for the D-1 group in general, including the two group. So are you only considering the split case with trivial Postnikov class?
Mm-hmm. I mean, we are also considering non-trivial Postnikov class. I tried to outline what the two representations are in one of the slides that I now lost. we discussed this also in a previous question. What happens when you have an integral positive class? This cochain that is not closed anymore and can be interpreted as associated in the property. Yes.
Sorry, I didn't hear you. So you're saying that you can only also consider non-trivial possible
Yeah.
class.
Yeah.
I see.
Yes.
Thanks.
Yes.
Okay, Eric, do you have a question?
Yeah, I have a quick question. How does decomposition enter this? I may have misunderstood what you're driving at, but in the conclusions and also in the introduction, you mentioned that your goal is to understand d-dimensional theories with finite d-1 form symmetries. And such a theory should decompose. In general, it'll be equivalent to a disjoint union of other quantum field theories in the same dimension without that higher form symmetry. How does decomposition therefore tie into this picture?
Yeah, I don't have a very concrete answer to this question, but what I can tell you is that if this decomposition, the decomposition procedure, based on what I've said, should be embedded into this higher representation theory of the dimensional group. It would be interesting to investigate how this works.
Eric, don't you need to go to a D group to get decomposition in D dimensions?
I might understand what you mean by a D group. So if I'm in 2 dimensions, for example, I'd want a 2-dimensional theory with what's called a 1-form symmetry group. So
but that's a 2 group, right?
Yeah.
That's right. And you guys mean something different.
So we want one lower than that. Yeah.
Oh, okay, fine. Then there's no decomposition, and life is much easier.
Yeah, right. Sorry. Yeah.
That's quite all right.
Yeah.
I mean, I think you should be able to consider things like that, Eric, but I think probably multi-fusion, that adjective will need to come in everywhere.
It would be part of my expectation as well. On the other hand, part of the structure of what was being described, part of the structure of 2 representations strikes me as possibly relevant, but I have some thoughts, but I don't want to waste everyone else's time. Perhaps someone else should ask a question.
Very good. Any more questions?
Yeah. Is it obvious the 2 category or the n-1 category you get is monoidal? Like,
I mean, obvious. What do you mean by obvious? So you're asking
like
whether
we expect the category we get has a fusion structure.
Yes.
Right. But for me, this is coming from, for example, for the condensation defect, this is the category of module categories over the things you want to gauge, something like that, right? And in general, this is not a fusion. Like, for example, what you wrote in the last slide, where you have vect G, like with alpha, right? And if you gauge this, you in general you won't get, unless this is a braided category, unless this has a braiding structure.
Right.
Otherwise, you don't get a fusion category.
Oh, right. Okay, so you're asking how general is the fusion adjective that we add to the categories after gauging when anomalies are present? Is that the question?
Yeah, and I mean, if in physics we expect to have a fusion category. I'm just asking what piece of mathematical input like guarantees that.
How about if I take the bimodule perspective instead, where I choose an algebra object and my higher category, and isn't it then obvious that one gets a monoidal structure, at least?
I guess so.
It's possible.
So there's some like discrepancy between gauging and condensation. Like there's some difference.
I mean, we want to claim that when we gauge these higher groups, condensations, the condensations that we get are already embedded in it. Now, I'm not entirely sure, to be honest, at the moment when we insert anomalies, whether so what guarantees that we will get full I mean, categories that are honestly confusion categories.
Okay.
I mean, but the expectation is that they are. I don't know.
I think it's because when you take your algebra objects, it's like if I have a monoidal category, that I take these kind of separable algebra objects and they give me kind of the objects and the representation. So this defines, this is equivalent to defining modules, right? So you have 2 vect G, you take the algebra objects. This is the same as finding modules for 2 vect G. So this is like a 3 vector space as a module for 2 vect G. And then what will happen if you have no anomaly, like, you have no full cocycle, then endomorphisms of the monoidal identity will be 3 rep of G. Oh no, so it's, no, sorry, it's, so you take all these algebra objects, bimodules, and blah, blah, blah. So you construct this condensation completion of 2 vect G. Then the monoidal identity will have endomorphisms of 2 rep G. And so your condensation is the bimodule map, which takes you from 2 vect of G to 2 rep of G via this kind of dual module, right? So you have this endomorphism of the identity in 3 rep of G. And this is one way to see your condensation picture. And then this endomorphisms of the identity naturally has a monoidal structure. And this is the monoidal structure you get for your condensation. I don't know if that makes sense, but that's one way to think about it.
No, yes, I think it does.
Thanks.
All right. More questions?
Yeah, I have a question about the higher representations. So is there a notion of, let me call it like higher characters or something for higher representations which classify?
Yeah,
Okay.
there is. Yeah.
I see. So, I mean, I was wondering, like, when we see a character table and try to reconstruct a group from it, it's not unique, right? We have strictly less information in the character table compared to the group.
Yeah.
If you consider this higher character table, which has maybe more information, like, is there some information, like, is there something known about how much of the group you can reconstruct from?
No, the only, I mean, I've just seen the results about computation of these 2 characters or higher characters. And I'm not sure whether has been made rigorous what kind of information is contained and what kind of information is lost.
I see.
Yeah.
I think my understanding is that the kind of higher characters come from putting the theory on a torus. If you think about a character coming from putting a theory on a circle, now you put it on a torus. So it's whatever you can reconstruct from whatever you can see from studying the theory on a torus. Okay. Well, let me stop the recording. Let's thank Andrea again.
Thank you.
Well, thanks a lot. And then we'll stop the recording. And if there are